Hello everyone, I am Rajarshi Roy and today I am going to talk about how one can explain complex systems using linear temporal logic even when the data we have may be noisy. This is a joint work with Jo-Raphael, Daniel, Ufuk and Shea. Nowadays, the systems being used in artificial intelligence are becoming increasingly complex. Understanding the functioning of such complex systems by humans is a rather challenging task. Thus, in order to assist humans to understand complex systems, we aim at learning human interpretable descriptions systematically by observing the behavior of such systems. Now let me show you how we provide descriptions of a system in a concrete example. So consider a system in which a robot follows a complex set of trajectories. Now this image here demonstrates one such trajectory of the robot. Now to provide simple descriptions of this system, we consider a setting in which we observe several trajectories of the robot. The trajectories are given as an input sample consisting of a set of positive examples that depict the desirable behavior of the robot and a set of negative examples that depict the undesirable behavior. Now based on these trajectories, we would like to infer a simple description of the system. In this example, a simple description which says that the robot is initially in position A and finally reaches position B is consistent with the information present in the sample, that is, it satisfies the positive traces and does not satisfy the negative ones. Now, the description that I just explained is in a formalism known as linear temporal logic or LTL. In the recent years, LTL has gained popularity as an explainable model since it can be translated to natural language easily. Moreover, it incorporates several temporal operators such as globally, eventually, and so on to capture temporal properties of systems. Using such operators, one can concisely describe a property such as whenever a request is made to the robot, it is eventually granted using a formula of this kind. Now for ease of representation, we would visualize LTL formulas using their syntax trees. Now the problem of LTL formula inference is a rather challenging one since the search space for LTL formulas is in fact infinite. Thus, to reduce the search space, most of the existing works rely on user-defined templates such as this to infer the prospective LTL formulas. So these approaches would only fill out placeholders in the templates with simple LTL formulas based on enumeration techniques. The main issue with these approaches is that they require the user to have prior knowledge about the underlying system. Now there are certain works that overcome this issue, in which they can actually learn formulas of arbitrary structure by performing systematic search over all LTL formulas. These approaches, however, are known to be not robust to noise in the data. So in particular, they tend to produce complex formulas and in an attempt to overfit the noise in the data. So contrary to existing works, our approach can infer arbitrary formulas and simultaneously is robust to noise in the data. Now we achieve this feat by solving the following problem. So given a sample consisting of a set of positive traces and a set of negative traces and a threshold, we would like to find a minimal LTL formula that has loss lesser than the given threshold. Now what is loss? So loss refers to the fraction of traces in the sample that the LTL formula misclassified. Now if you might have observed, there are two important aspects of this problem. First, the allowed misclassification ensures that the LTL formula we obtain is actually robust to noise in the data. Moreover, the minimality criteria ensures that we obtain concise and human understandable formulas. Now to solve this problem, we propose two novel algorithms. The first one is a MaxSAT based algorithm that infers minimal LTL formulas. The second one is a decision tree based learning algorithm that uses MaxSAT based algorithm as a subroutine. So in this algorithm, we in fact trade off minimality of the formula to obtain faster termination. Now we have implemented both our algorithms in a tool, and we have observed that our algorithms can successfully infer small formulas from noisy samples. So now I will describe our algorithms in greater detail, starting with the first one. So our first algorithm essentially converts the inference problem into a propositional formula phi Sn. So this propositional formula enables us to check whether there is an LTL formula of size n that is consistent, that has a loss less than the threshold. Now internally, this formula phi Sn consists of two types of constraints. The first type of constraints are called hard constraints, and one necessarily needs to satisfy them. So these constraints include constraints that ensure that the prospective LTL formula has a valid structure and is of size n. Moreover, we have constraints that ensure that the prospective LTL formula evaluates the examples in the sample based on valid LTL semantics. Now the second type of constraints we have is called soft constraints, and one needs to maximize the number of such constraints that one can satisfy. So these constraints include constraints that ensure that the prospective LTL formula satisfies the positive traces and the prospective LTL formula does not satisfy the negative ones. Now we would use MaxSAT solvers to find assignments to phi Sn. Now using a MaxSAT solver, we would find assignments to phi Sn for increasing values of n to search for LTL formulas of the appropriate size that has loss less than the given threshold. Now this algorithm guarantees that we obtain a minimal LTL formula. However, the time required for finding assignments to phi Sn increases exponentially with n. Thus, to speed up the inference process, we combine this algorithm with a decision tree learning algorithm, which I will present next. So in the decision tree learning algorithm, we infer decision tree over LTL formulas, which is nothing but a decision tree in which the decision nodes are LTL formulas. So one can even construct an equivalent LTL formula for a given decision tree over LTL formulas. So in our algorithm, we infer decision tree by exploiting classical decision tree learning algorithms such as ID3. I will briefly touch upon the two main steps in the algorithm. First, for the decision nodes, we infer concise LTL formulas using a MaxSAT based algorithm. So what we do here is essentially search for LTL formulas based on certain metrics that ensure that the size of the inferred LTL formula does not grow too large. We then split the sample based on the inferred LTL formula, and we recursively apply the decision tree learning algorithms. While in this algorithm we do not ensure we obtain a minimal formula, we observed empirically that our algorithm terminates faster while inferring formulas from noisy data. Now we have implemented a prototype of both our algorithms. Further, we have compared our algorithms against the state-of-the-art LTL learning tool by Nider and Gavran, which we refer to as SATFLI. So we essentially wanted to evaluate the performance gain our algorithms achieve in the presence of noise. To provide a glimpse of the experiments, I will demonstrate one of the comparisons in which we compare our first algorithm, that is MaxSAT with SATFLI. So first and foremost, we observed that a considerable improvement in the running time performance by our algorithm, as you can see from the chart. The instances in the lower half of the chart are the ones in which our algorithm ran faster. So our algorithm in fact performed faster in actually 144 instances out of 148 noisy samples that we consider. Further, we compared the size of the formula inferred by our algorithm, and here we observed that we always obtained a formula that is smaller or equal in size than the one obtained by SATFLI. Again, from the chart it is evident that we do so, and the ones in the lower half represent the instances in which we actually obtained a smaller formula. Now I would like to conclude by saying that in this work we presented two novel algorithms for inferring LTL formulas from noisy data, and we have also established empirically that we can actually do so. Thank you for listening. Questions?